In this lab, we were asked to separate a mixture into its separate dye components and identify those components using the graphical representation of the Beer-Lambert law. The Beer-Lambert law is an equation that shows the direct relationship between absorbance and concentration. It can be seen in the equation A equals epsilon times B times C. A is absorbance, epsilon is the slope of the graph of a Beer-Lambert plot, B is the path length, which is usually 1 centimeter, and C is the concentration. The absorbance can be measured with a spectrophotometer. Epsilon is the slope of a graph of concentration versus absorbance. B is usually 1 centimeter, or it can be the path length of your cuvette. And concentration can either be derived from M1V1 equals M2V2, or the moles over the liters of whatever solution you have. Lambda max corresponds to the wavelength of maximum absorbance. In this lab, there are 2 reasons why we need to scan for lambda max across all wavelengths. 1, because all of our solutions are different colors, therefore they absorb different wavelengths, and 2, to find the highest point across all wavelengths, meaning we find the absolute lambda max, not just an estimate across a certain range. Let's look at this week's lab. Once we separated the dye mixture, we put the first color transitioned between the two and the secondary color of the solution into separate cuvettes and included a blank of distilled water to zero the machine. Failure to zero the machine with the distilled water blank would lead to inflated absorbance values because the machine is not starting off reading from 0. It is also very important to fill your cuvettes to the fill line seen here. We brought over the cuvettes to the spectrophotometer and began setting up and collecting data. First, we zero the machine by cleaning the distilled water-filled cuvette with a ChemWipe, putting it into the machine and clicking the 0 button, making sure that the red numbers on the top left are close to 0. Next, we clean our first sample with another ChemWipe, put it into the machine and click the Start button. The machine will scan the sample from 200 to 800 nanometers to help us find the lambda max. We graphed the next 2 samples in the same way as the first and took a picture of our graph to compare them to the graphs presented to us on a worksheet in class. In our final graph, you can see 3 separate lines for our 3 separate solutions. Each line has a different peak representing its lambda max. The lambda max is the optimum wavelength for the maximum absorbance. Finally, we copied key notes into our lab notebooks to study for our final. Thank you for watching!